First of all, I would like to thank you for giving me this opportunity to present my work. Also, I would like to thank everyone here for your presence and interest in my work. My name is Saeid. I'm a researcher at Political University of Madrid. I obtained my PhD at the same institution under supervision of Professor Manuel Pastor. And my research interest lies in the area of computational modeling and propagation modeling using meshless methods such as SPH. And today I'm going to present you a computational propagation model that can be applied to reproduce the complex dynamic behavior of fast landslide. Introduction. A fast landslide is a geological phenomenon and happens when a large mass of land slides or followed by natural processes or human action. They have this ability to travel a long distance in a very short time and reach areas that initially considered safe. Fast landslide happen frequently in mountainous region or along river, causing economical damage and many casualties around the world. And due to climate change and growing population in high-risk area, risk assessment of fast landslide using continuous dynamic models implemented in advanced simulation tools is becoming more important. In order to assess the risk and design the possible countermeasures, it is essential to have a better understanding of these phenomena as mechanism. Mathematical model. In flow-like landslide, the dynamic of soil is governed by a set of equations consisting of balance of mass equation and balance of linear momentum equation, and then these balance equations are completed using suitable constitutive and kinematic relations. As you know, three-dimensional formulation of mathematical model is usually expensive in terms of calculation time, and these models can be simplified and reduced to two-dimensional formulation through depth integrated approximation. Since flow-like landslide has a small average depth in comparison to their width and length, their governing equation can be integrated along depth, and the resulted two-dimensional depth integrated model can provide a good relation between accuracy and time consumption. One-phase model. In our model, actually, the simulations are presented in this way because in depth integrated model, the particles cannot be defined along the depths. And in these models, the flowing mass is divided to a finite number of columns that represent by particle. And as you can see here in one-phase model, actually the phases are simulated in only one layer. Firstly, there is a balance of mass equation consisting of variables such as height, velocity, and erosion rate. The second equation is balance of linear momentum. On the right-hand side of the equation, the first term is the gradient of the pressure, and the rest are the source terms. This tau b is a Basel shear stress, depends on the rheological laws considered. This B is the body force, and also the bed entrainment or soil erosion can also be considered in this model by its implementation in source term of balance of mass equation, and this erosion rate can be calculated by using a suitable entrainment laws. In this model, the balanced equation are discretized by using a smoothed particle hydrodynamic or SPH, which is a Lagrangian meshless method, and it is used to discretize the flowing mass into a set of particles, each having individual material property. These particles interact through a kernel function that calculates the relevant property on each particle over neighboring particle. When all the information is stored to these moving node or particles, then this kernel approximation can be converted to a discretized form of summation over all the particles inside the support domain. And now a set of ordinary differential equations is obtained in discretized form with respect to time. Next, we analyze a simple dam break problem. In dam break problem, we assume that the flowing material is contained between two walls, and once the wall on the right side collapses, the material liquefies and propagates over a horizontal plane. And in this animation, we have provided the total profiles of the total heights of the flow at different time steps during the propagation. Here, the numerical analysis of frank rock avalanche was performed through the proposed one-phase model. As you can see, the flowing material could well spread over all the observed impacted area and almost cover the whole trim line. Two-phase model. In two-phase model, the phases are simulated in different layers, but these layers interact with each other through a drag load that depends on the permeability and porosity of the soil. Fast landslide particulate debris flows are characterized by the coupling between solid and porphyroid phases. In order to simulate such phenomena, a two-phase model should be applied to reproduce the motion of both phases during the propagation stage. As you can see here, the governing equation consists of two balance of mass equations, and some of the variables were denoted by sub-indexes S for the solid phase and W for the fluid phase. In two-phase model, two new terms have been implemented in balance of linear momentum equation. This term describes the porosity variation, and this term describes the interaction between the phases. And this interaction force can be calculated by using a suitable drag load. In two-phase model, the balance equations are also discretized by using SPH method, where a double set of nodes is defined, one to represent the movement of the solid particle and another to represent the movement of the fluid particle. Here we have provided the profiles of total height and porosity corresponding to the dam break problem with very low soil permeability. And as you can see, the velocity of both phases are very similar to each other, and porosity, which is 0.6 at the initial step, remain constant during the propagation stage. Here we have compared two numerical code to simulate Acheron rock avalanche happen in New Zealand in ancient history. These two widely validated numerical codes are geoflow and overflow, which are based on similar mathematical equation depth integrated two-phase model, but with fundamentally different numerical solver. And in this article, we have compared the numerical result with field data, and the result of both code can be considered satisfactory. Two-phase model considering pore water pressure evolution. In this model, the balance of mass equations remain unchanged. But in a balance of linear momentum equation, there is a term describing the pore water pressure evolution, and this delta P is the excess pore water pressure, and it should be calculated at each node and time step. As you know, in depth integrated model, the vertical structure of magnitude is such as pore water pressure is disregarded. And one important aspect of fast landslide is pore water pressure generation due to a strong coupling between solid and pore fluid phases. For this reason, in the proposed model, a consolidation equation is used to describe the pore water pressure along depth, and it has the diffusion term that is discretized by making two changes: height variation and porosity variation. This consolidation equation is discretized by using finite difference method, and this SPH finite difference model contributes to enhancing the proposed two-phase model by adding one dimension of finite difference mesh into each SPH node that represents solid particle in order to improve the description of the pore water pressure along depth. In this dam break problem, we changed the scenario by assuming that a permeable screen or a permeable train is located beside the source material. And this figure shows the distribution of relative pore water pressure along depth. As you can see, the relative pore water pressure at the basalt surface is 1, indicating that the material is fully liquefied. In this animation, you can see that the basal pore water pressure over the permeable screen is dissipating. But pore water pressure still exists on the body of the landslide, and this SPH finite difference model is capable of considering such behavior. Two-phase two-layer model. This figure shows a column of soil where a saturated layer exists at the bottom and unsaturated layer at the top. And total height is divided to a three layer: solid, fluid, and air. And this alpha is the relative height. And in this, actually in this extended model, this vital parameter of relative height has been implemented in balance of mass equation for the fluid phase in order to take into account the phenomena of the watering and the saturation during the propagation stage. Also, this parameter relative height has been implemented in balance of linear momentum equation in order to consider the effect of the watering and the saturation. In two-layer model, the hydrostatic pressure and excess pore water pressure actually are considered for the saturated layer, and a null pore water pressure is assumed for the layer above the water table. And this modified consolidation equation also contributes to enhancing the description of the pore water pressure for the partially saturated soil. And here we have provided the profiles of total height and porosity corresponding to a dam break problem with a very large permeability. And as you can see, the initial porosity is 0.6, and it is evolving during the propagation stage. At the front side of the flow, the porosity reaches the value of 1, indicating that the water has abandoned the solid skeleton. And at back side of the flow, you can see that the porosity is decreasing until it reaches its minimum value, which is 0.4 here. And after this point, the saturation starts at the rate that depends on the permeability of the soil. Popocatépetl is an active volcano near Mexico City. In 2001, there was a lahar as a result of glacier melting, and this lahar traveled a long distance, around 14 kilometers, before reaching a village around here. And this article mentioned a few times that this phenomena of dewatering has been observed in this case. And this animation shows the propagation heights of the solid phase and fluid phase corresponding to this Popocatépetl case. And as you can see here, the fluid phase actually is leaving the solid particle. Actually, in this case, the lahar behaved as a debris flow at initial stages of the propagation. But after the phenomena of dewatering happened, this lahar behaved as debris flow throughout the propagation until the deposition. Two-phase two-layer model considering inflow rate. In this extended model, this vital parameter of water inflow or inflow rate is actually implemented in balance of mass equation for the fluid phase in order to consider water infiltration caused by rainfall or bed entrainment. And this term has also been implemented in balance of linear momentum equation to consider the effect of water inflowing the flowing mass. And as you know, this volume turbulence coefficient is a parameter used in volume rheological model, and for most typical cases, a constant volume coefficient could provide a reasonable approximation. But for a specific scenario where changing in soil conditions significantly impact on the behavior of the flow, a variable volume coefficient is more appropriate. And that's why we have proposed this water content dependent volume rheological model, in which the volume coefficient depends on the porosity of the soil. In this dam break problem, we assume that the rain causes the water flow into the mass as it propagates. And this actually water inflow rate of 0.5 meter per second is introduced in order to observe its impact on the front evolution. And this animation shows how porosity and volume coefficient changes during the propagation and how water inflow affects on them. And this result emphasizes the significant impact of considering water inflow in landslide propagation analysis. When water infiltrates the flowing mass, it changes the soil properties such as water content, solid concentration, which profoundly affect on the runout distance of the flow. Pikachu landslide happened in El Salvador in 1982. The filtration of a large amount of water due to rainfall caused these flow slide. As you can see in this animation, if we use a very low and constant volume coefficient, you can see that the flowing material is not able to cover the whole trimline of the impacted area. And if we use an average and constant volume coefficient, you can see that a large amount of material flow down outside the impacted area. But if we use this, water content dependent rheological model, you can see that the flowing material could well spread over all the observed impacted area and cover the whole trimline. Conclusion, the two-phase model is able to apply to the cases where solid particles and water can have a different velocity, and the model is able to include the velocity of both phases. The two phases model, considering excess pore water pressure, correctly perform the time-space evolution of the pore water pressure during the whole propagation stage, from initiation to propagation over an impermeable and permeable bottom boundary. And two-phase, two-layer model is able to cope with two important issues in landslide propagation modeling: dewatering and water inflow. And thank you so much for your attention. If you have any question, I will be happy to answer.